to have a greatest ability to attract electrons, nothing but the electronegativity, for the first time mentioned by Pauling. Approximate value for electronegativity for few elements are given below. Very important. I will show you in the table. Electronegativity of a given element is not constant. Why? Because when it is varying depending on the element to which it is bound, it is varying from compound to compound. It is not a measurable quantity. Perhaps it does provide a means. It does provide a means of predicting the nature of force that holds a pair of atoms together. Okay, a relationship. Just like electronegativity generally increases across a period from left to right in the periodic table, from lithium to fluorine. And very important point, and it is decreases down a group, say from fluorine to astatine in the periodic table. How can these trends be explained? These trends can be explained by electronegativity be related to basically atomic radius. It is closely related to atomic radii, which tend to decrease across each period from left to right, but increase down which in each group. But why? Attraction between outer or valence electrons and the nucleus increases as the atomic radius decreases in a period. Electronegativity also increases across in this manner. If you carefully see this diagram, electron gain enthalpy, ionization enthalpy, and whereas ionization enthalpy, electron gain enthalpy, atomic radius, electronegativity, atomic radius, both are opposite in direction, which means non-metallic character and metallic character in the periodic table. You can imagine this is a periodic table. So non-metallic character increases when you go down from bottom to top. Metallic character increases from this direction to bottom direction. So at the same time, electron gain enthalpy generally you can see from this direction to this direction. Ionization enthalpy you can see from this direction to this direction. So a period trends elements in the periodic table in case of electronegativity and atomic radii. Now let us continue the remaining part. Electronegativity values on Pauling scale across the periods. Atom, let us take period 2. Electronegativity, atom, period 3, electronegativity. Let us take period number 2 and some of the elements and their electronegativity. Lithium 1.0, beryllium 1.5, barium 2.0, which means constantly electronegativity increases from lithium to fluorine. Whereas atom, period number 3, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. What happens here? Electronegativity increases from sodium to magnesium, aluminum, silicon. Gradually it is going to be increased. So this is an increasing direction in period number 3. So let us take group 1, electronegativity value on Pauling scale down a family. This is an increasing across the periods, and whereas electronegativity value on Pauling scale down a family. Atom group number 1, lithium, sodium, potassium, rubidium, cesium, and electronegativity value 1.0 for lithium, 0.9 for sodium, potassium 0.8, rubidium 0.8, cesium 0.7. Atom group number 17. If you take fluorine, it is 4.0, for chlorine 3.0, for bromium it is 2.8, for iodine it will be 2.5, for other elements as you can see here. Now in case of to gain electrons, therefore electronegativity is directly related to non-metallic properties of the element. And what about, it can be further extended to say that electronegativity is inversely related to electronegativity related to the metallic properties of elements, which means thus the increase in electronegativity across a period, if electronegativity is going to be increase, what will happen across a period? It is accompanied by increasing, what will happen in non-metallic properties and decreasing in metallic properties of elements. Similarly, the decrease in electronegativity, what will happen if electronegativity decreases down to a group, is accompanied by decrease in metallic property. Okay. So increase in metallic property of elements is accompanied by decrease in non-metallic properties or increase in metallic properties of elements in the opposite direction. So all these periods trends are summarized in figure number 3.7, 3.72. Period trends in chemical properties. What are they? Most of the trends in chemical properties of elements, such as diagonal relationship, which helps to form a compound, inert pair effect to form a compound, effects of lanthanoid contractions, etc. Will be dealt with along with the discussion of each group in later units. In this section, we shall study the periodicity. Let us take what is periodicity. We are going to see periodicity of valency state shown elements and the anomalous properties of the second period elements, from lithium to fluorine, periodicity, valency or oxidation states. Periodicity of valence of oxidation states. The valency is the most characteristic property. It is the most characteristic property of the elements. These elements can be understood in terms of their electronic configurations that we have seen in the previous classes. Valency, if you carefully observe it, a representative element is usually, though not necessary, which means it is not equal to the number of electrons, but perhaps in the outermost shell, if you carefully see, orbitals are equal to minus or number of outermost electrons. Now here chemistry with outermost electronic configuration 2s2, which means 2s2 and 2p5 shares one electron with oxygen, going to share electron with oxygen in OF2 molecule. So being highest electronegative element, fluorine is given oxidation state -1, and since there are two fluorine atoms in this molecule, if you take the oxygen with outermost electronic configuration 2s2 and 2p4 shares 2 electrons with fluorine atoms and thereby exhibit oxidation state +2. And whereas in Na2O, oxygen being more electronegative, oxygen is more electronegative, accepts 2 electrons, one from each 2 sodium atoms, that shows oxidation state as -2. So finally what I am telling you, on the other hand, sodium is there now. Sodium with electronic configuration 3s1 lost 1 electron and 2 oxygen and given oxidation state as +1. So thus oxidation state of element in particular compound can be defined as the charge, specific charge, plus or minus, acquired by its atom, whether oxygen, okay, or whether sodium, etc. Electronegativity consideration from other atoms in the molecule will be varied from compound to compound. So problem, using the periodic table, predict the formula. We have to find out the formulas of compound which might be formed by the following pairs of element. Silicon is there, bromide is there, aluminum is there, sulfur is there. So if you take solution, silicon is a group 14th element with valency of 4. So bromide belongs to halogen family with valency of 1. So we can say that for bromide is belongs to halogen family. Okay. Finally, what I am telling you, hence the formula for compound formed would be silicon bromide. Okay. And aluminum, if you take one more statement is there, no? Aluminium is there, na? Aluminium belongs to 13th group element, no, with a valency of 3, and sulfur belongs to, if you take sulfur, belongs to 16th element with a valency of 2. So what we can say finally, hence the formula for this is Al2S3, which is a compound. Nowadays the term oxidation, if you take a state, is frequently used for valency. Now consider two oxygen containing compounds. OF2 is there, Na2O is there. The order of electronegativity of the three elements that are involved here. So fluorine, oxygen, sodium, each of atoms of fluorine. Finally, some periodic trends observed in valence of elements such as hydrides, potassium hydride, sodium hydride, and oxides are shown in the table. Other such periodic trends which occur in the chemical behavior of elements are discussed elsewhere. So here you have a group 1, 2, group 2, group 13, 14, 16, 17, 18. Number of valency for group 1, 1, group 2, 2, group 13, 3, group 14, 4. Valency of electrons. And lengths 1, 2, 3. Then such like that it is given for various groups. And after that, periodic trends in valency of elements. Okay, group formal hydrates and formal oxides. Lithium hydride, sodium hydride, potassium hydride, calcium hydride, barium hydride, aluminum hydride. Okay, like that, silicon hydride, and you can see here, and the remaining you can see here for group 17. So hydrochloric acid in group 17, hydrogen bromide, hydrogen iodide, hydrogen fluoride, etc. So formula for oxides: lithium oxide, sodium oxide, potassium oxide, and whereas in group 2, magnesium oxide, calcium oxide, strontium oxide, barium oxide. In group 13, barium and aluminium, Al2O3, aluminum oxide, and gallium oxide, Ga2O3, and other things. In group 14, as you know that carbon dioxide is there, silicon dioxide is there, and GeO2 is there, and strontium oxide is there, and lead oxide is also there. So whereas in group 16, sulfur trioxide, ceruleum trioxide, and beryllium trioxide is there, and Cl2O7 it is there in the group 17. So these are very, very important formulas. Anomalous properties of second period elements, what are they? First element of each group, let us take lithium, and second group will be beryllium. Group 13 to 17, which means boron to fluorine, differs in many respects from other members of their group. For example, lithium, unlike other alkali metals are there, beryllium is there, and unlike other alkaline earth metals, form compounds which are pronounced as covalent character. So predominantly form ionic compounds. So metallic radius M by Pm, lithium for lithium element, and for beryllium, boron, you can see here. For sodium 186 is there, magnesium 160, aluminum 143. Ionic radius M by Pm. For lithium 76 m by pm. Okay, like that it is given. Finally, what I am telling you, second element of the following groups, magnesium and aluminium respectively, similar is compound referred to as diagonal relationship in the periodic properties. So what are the reasons for different chemical behavior of the first member of a group, S and P blocks? The anomalous behavior is attributed to their small size. It says about size, small size, large charge, radius ratio and high electronegativity of the elements. First member of group has only 4 valency orbitals, that are 2 s orbitals, 2 2p orbitals, and available for bonding, whereas second member of the group have 9 valency orbitals, 3 are s, 3 are p, 3 are d. Okay, and finally, as consequence of this, maximum covalency of first member of each group is 4. Example, boron is there. Boron can only form Bf4, whereas other members of group can form or expand their valency shell to accommodate more than 4 pairs of electrons. So example, aluminum AlF6, okay, to form specific compound. Further, first member of p block elements display greater ability to form pi bonds. Okay, so p pi bonds, multiple bonds to itself. Example, C double bond C, C triple bond C, and N double bond N, N triple bond N. Two other second periodic elements, example, C double bond O, C double bond N, C triple bond N, N double bond oxygen, compared to sequence members of the same group. Carbon with double bond of oxygen, carbon with double bond of nitrogen, carbon with triple bond of nitrogen, nitrogen with double bond of oxygen with the same group. Problem number 3. Oxidation state covalency of aluminium, aluminium chloride, okay, H2O5, okay. So this is a compound given here, and 2 plus same is given, and what will be the answer for that? No oxidation state of aluminium is +3, and the covalency is approximately equal to 6. And finally, what I am telling you, periodic trends and chemical reactivity, we have observed that if we take periodic trends in certain fundamental properties such as atomic and ionic radii. So ionization enthalpy, electron gain enthalpy, valency, we know that periodicity is related to